Welcome to Zain Facts Channel. Today we're diving into one of the most enigmatic and mind-blowing phenomena in the universe, black holes. Buckle up because we're about to journey beyond the event horizon and uncover the fun, fascinating, and downright incredible facts about black holes. This comprehensive guide will cover everything from their formation and anatomy to the latest discoveries and theories that challenge our understanding of these cosmic wonders. Chapter 1. What is a black hole? Black holes are regions in space where the gravitational pull is so intense that nothing can escape it, not even light. This makes black holes invisible to the naked eye and detectable only through their effects on surrounding matter and light. Black holes are formed when massive stars reach the end of their life cycle and collapse under their own gravity. This collapse compresses the star's core to an incredibly dense point known as a singularity, where gravity is infinitely strong. Surrounding this singularity is the event horizon, the boundary beyond which nothing can return. 1.1. The formation of black holes. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. For stars with a mass greater than about 20 times that of the Sun, this collapse results in a supernova explosion, leaving behind a dense core. If this core's mass is more than about 3 times that of the Sun, it continues to collapse into a black hole. There are two main types of black holes based on their formation: stellar black holes. These are formed from the remnants of massive stars after a supernova explosion. Supermassive black holes. These reside at the centers of galaxies and have masses millions to billions of times that of the Sun. The exact formation process of supermassive black holes is still a subject of research and debate. 1.2. Anatomy of a black hole. A black hole has 3 main parts. 1. The singularity, the core where the mass is concentrated and gravity is infinitely strong. 2. The event horizon, the boundary beyond which nothing can escape. 3. The accretion disk, the swirling disk of gas and dust that heats up as it spirals into the black hole. The event horizon marks the point of no return. Once an object crosses this boundary, it is pulled inexorably toward the singularity. The accretion disk is often incredibly bright due to the intense heat generated by friction as matter spirals inward. Chapter 2. Types of black holes. There are 3 main types of black holes, each with distinct characteristics and formation processes. Stellar black holes are formed from the remnants of massive stars. When a star with a mass greater than 20 times that of the Sun exhausts its nuclear fuel, it undergoes a supernova explosion. The core that remains can collapse into a black hole if it is more than about 3 times the mass of the Sun. Stellar black holes typically have masses ranging from about 3 to 20 times that of the Sun. They are often found in binary systems, where they can accrete matter from a companion star, leading to the formation of an accretion disk and emitting X-rays. Supermassive black holes found at the centers of galaxies have masses millions to billions of times that of the Sun. The formation of supermassive black holes is a topic of active research. One theory suggests they form from the direct collapse of massive gas clouds in the early universe, bypassing the star formation stage. Recent discoveries by the James Webb Space Telescope, or JWST, have provided new insights into the formation of supermassive black holes. Some evidence suggests that these black holes might have formed much earlier in the universe's history than previously thought, within the first billion years after the Big Bang. Intermediate black holes are a rare and elusive type, with masses between stellar and supermassive black holes, typically ranging from 100 to 100,000 times that of the Sun. Their existence was confirmed through the detection of gravitational waves from the merger of 2 intermediate black holes. The formation of intermediate black holes is not well understood, but they might form through the merging of smaller black holes or the collapse of massive star clusters. Chapter 3. The Formation Mysteries. One of the biggest mysteries is how supermassive black holes formed so quickly after the Big Bang. Recent findings from the JWST suggest that some black holes might have formed from the collapse of massive clouds of gas and dust directly into black holes, bypassing the usual stellar evolution process. These early black holes could have grown rapidly by accreting vast amounts of matter and merging with other black holes. This rapid growth could explain the existence of supermassive black holes in the early universe. Chapter 4. Feeding Frenzy. Black holes grow by accreting matter from their surroundings. This process is incredibly energetic, causing the material in the accretion disk to heat up and emit powerful radiation, often making black holes some of the brightest objects in the universe. Accretion disks form when a black hole pulls in matter from a companion star or the interstellar medium. The material spirals inward, heating up due to friction and gravitational forces. This process can release enormous amounts of energy, making accretion disks visible across vast distances. Quasars are supermassive black holes with extremely luminous accretion disks. They are among the most energetic objects in the universe, capable of outshining entire galaxies. Quasars were more common in the early universe when black holes were rapidly growing and accreting matter. Black holes can influence their surroundings through feedback mechanisms. The powerful outflows of radiation and particles from accretion disks can regulate star formation in the host galaxy. These feedback processes can either trigger or quench star formation, affecting the evolution of galaxies. Chapter 5. Black holes and galaxies. Supermassive black holes have a symbiotic relationship with their host galaxies. They can influence galaxy formation by regulating star birth through their immense gravitational pull and energetic outflows, which can either trigger or quench star formation. Most, if not all, galaxies harbor a supermassive black hole at their center. These black holes can shape the structure and dynamics of their host galaxies. The Milky Way's supermassive black hole, Sagittarius A, is located at the center of our galaxy and has a mass of about 4 million times that of the Sun. Galactic mergers and interactions can lead to the growth of supermassive black holes. When galaxies collide, their central black holes can merge, forming an even larger black hole. These mergers can trigger intense periods of star formation and reshape the galaxies involved. Black holes can regulate star formation through feedback mechanisms. The powerful outflows of radiation and particles from active galactic nuclei, or AGN, can heat the surrounding gas, preventing it from collapsing to form new stars. This process can quench star formation and influence the evolution of galaxies. Chapter 6. The Event Horizon Telescope. In 2019, the Event Horizon Telescope, or EHT, captured the first ever image of a black hole located in the galaxy M87. This monumental achievement provided direct visual evidence of a black hole's event horizon and opened new avenues for studying these enigmatic objects. The EHT is a network of radio telescopes around the world that work together to create a virtual telescope the size of Earth. This collaboration allows astronomers to achieve the resolution necessary to image the event horizon of a black hole. The first image of a black hole, captured in 2019, shows a bright ring of light surrounding a dark shadow. This shadow is the event horizon, beyond which nothing can escape. The bright ring is the accretion disk, where matter heats up and emits radiation as it spirals into the black hole. The success of the EHT has paved the way for future observations of black holes. Researchers aim to capture images of other black holes, including Sagittarius A, and to study the dynamics of accretion disks and relativistic jets in greater detail. Chapter 7. Time Dilation and Spaghettification. As you approach a black hole, the effects of gravity become extreme. Time dilation causes time to slow down significantly, and if you get too close, you'd experience spaghettification, where tidal forces stretch you into a thin, elongated shape. Time dilation is a consequence of Einstein's theory of general relativity. Near a black hole, the intense gravitational field slows down time relative to an observer far away. This means that if you were to orbit close to a black hole, you'd experience time much more slowly than someone further away. Spaghettification occurs when the tidal forces near a black hole stretch objects into long, thin shapes. This happens because the gravitational pull is much stronger at one end of the object than at the other, causing it to be stretched out into a thin, spaghetti-like shape. If a person were to fall into a black hole feet first, the gravitational force on their feet would be much stronger than on their head, resulting in spaghettification. Chapter 8: Black Holes and Quantum Mechanics. Black holes sit at the intersection of quantum mechanics and general relativity, two of the most fundamental theories in physics. The study of black holes is not just about understanding these enigmatic objects, but also about seeking a unified theory of physics. One of the most puzzling aspects of black holes is the information paradox. According to quantum mechanics, information about the state of a physical system must be preserved. However, if something falls into a black hole, it appears that the information about its state is lost forever, violating this principle. Physicist Stephen Hawking proposed that black holes could emit radiation, now known as Hawking radiation, which could allow them to slowly lose mass and eventually evaporate. However, whether the information about the objects that fell into the black hole is preserved or lost in the radiation is still a topic of intense debate among physicists. Hawking radiation arises from quantum effects near the event horizon. According to quantum theory, pairs of virtual particles constantly pop in and out of existence. Near the event horizon, one of these particles can fall into the black hole while the other escapes, making it appear as if the black hole is radiating particles. This process would cause the black hole to lose mass over time and potentially evaporate completely. Understanding black holes also involves the quest for a theory of quantum gravity, which would reconcile general relativity and quantum mechanics. String theory and loop quantum gravity are two of the leading candidates for such a theory. Black holes provide a natural laboratory for testing these ideas, as they involve both strong gravitational fields and quantum effects. Chapter 9: Recent Discoveries and Future Research. The study of black holes is one of the most exciting and rapidly evolving fields in astrophysics. Recent discoveries and future missions promise to deepen our understanding of these fascinating objects. The James Webb Space Telescope has made significant contributions to our understanding of black holes. It has observed the early universe in unprecedented detail, providing new insights into the formation and growth of supermassive black holes. Some findings suggest that these black holes formed much earlier than previously thought, within the first billion years after the Big Bang. This challenges existing theories and opens up new questions about their origins. The detection of gravitational waves by the LIGO and Virgo observatories has opened a new window into the study of black holes. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes. These observations have confirmed the existence of intermediate black holes and provided new insights into the dynamics of black hole mergers. The Event Horizon Telescope's first image of a black hole was a groundbreaking achievement, but it is only the beginning. Future observations aim to capture images of other black holes, including Sagittarius A at the center of our galaxy. Researchers also plan to study the dynamics of accretion disks and relativistic jets in greater detail, which could provide new insights into the physics of black holes. Several upcoming missions promise to revolutionize our understanding of black holes. The Laser Interferometer Space Antenna will detect gravitational waves from space, providing a new way to study black hole mergers. The Square Kilometer Array will be the largest radio telescope ever built, capable of detecting the radio waves emitted by black holes and other cosmic phenomena in unprecedented detail. Chapter 10: Fun and Fascinating Facts about Black Holes. Black holes are not just mysterious and mind-blowing, they are also a source of endless fascination. Here are some fun and intriguing facts about black holes. The intense gravitational field near a black hole causes time to slow down relative to an observer far away. This effect, known as time dilation, is a consequence of Einstein's theory of general relativity. If you were to orbit close to a black hole, you would experience time much more slowly than someone further away. Black holes can rotate, and their spin affects the surrounding space. A rotating black hole drags space-time around with it, a phenomenon known as frame dragging. This effect can be so strong that it twists the path of particles and light around the black hole. Although black holes are known for their ability to devour anything that comes too close, they can also slowly lose mass and evaporate over time through a process known as Hawking radiation. This process takes an incredibly long time for large black holes, but it suggests that black holes are not entirely eternal. When two black holes come close to each other, they can merge to form a single, larger black hole. This process releases a tremendous amount of energy in the form of gravitational waves, which can be detected by observatories like LIGO and Virgo. Supermassive black holes at the centers of galaxies play a crucial role in shaping their host galaxies. Their powerful gravitational forces and energetic outflows can regulate star formation and influence the structure and evolution of galaxies. Black holes are one of the most fascinating and mysterious phenomena in the universe. They challenge our understanding of physics, push the boundaries of scientific discovery, and captivate our imaginations. From their formation and anatomy to the latest discoveries and theories, black holes offer a glimpse into the extremes of nature and the depths of our universe. Thank you for joining us on this journey through the cosmos. Don't forget to like, subscribe, and hit the bell icon for more mind-blowing content from Zain Facts channel. Stay curious and keep exploring the wonders of the universe. Until next time, keep looking up and wondering about the incredible universe we live in.